Okay, so today we're going to talk about descriptive statistics, describing your data. So that's the slides, that's the notes. So we start from data. From data, we retrieve information. So from the data to information, this stage is meant to describe the data, whatever it is. From here, we go for the later classes to facts and knowledge. So right now, we're going to talk about this area. From data, how to derive information. Next. So this is called descriptive statistics. From the population, we draw a sample. Let's say the population, we want to study a variable X. Example, you want to study what is the average BMI among a group of people. What's the average marks students obtain? So these kind of things. What's the average distance traveled, right? Or what is the prevalence of a disease? So we go into that. So can we study? Now, can some of you share what you're studying? Anyone? Your area of research? Yeah.
The level of persistence in year 3 students.
Persistence in?
Year 3 students.
Year 3.
Yep.
Right. Persistence among students.
Yep.
Okay. How do you measure persistence?
We don't know yet.
Okay, let's say a scale, okay? Let's say on a score of 0 to 100, let's say you measure persistence through an instrument, okay?
Yes.
Right. So you want to know what's the level of persistence among students? How many students are there?
100.
100. No, in the population, there are many students, right?
Yeah, sorry, in the sample group, there are 100.
Right.
But,
population, talking of population. Your objective is to persistence among the students, right? Let's say there are 10,000 students there. Can you study all the 10,000 students?
Nope.
Why cannot?
Too many.
What's the term you use?
If we want to do an experiment with them, so I can't put 10,000 through an experiment.
We call it ETC. Remember the last class we called ETC? What's ETC?
No idea.
Energy, time, and cost.
Okay.
Takes a long time.
We are not able to study the entire population.
Yeah.
Then what do you do? We take a sample.
Yeah.
Right. The sample, let's say we take 100 students. Population very large, maybe there are 10,000 students. We can't study the entire 10,000 because of ETC, we take a sample. So in the sample, we are able to measure whatever we need to measure, right? Example, height of students, weight of students, BMI, persistency of the students. We can measure them. 100 students. Possible? Right. Next step is what? Describe example, the level of persistence. Describe. So to describe, first need to know how the variable was measured. Was it quantitative or qualitative? Example, marks. Marks obtained by students. Quantitative or qualitative? Marks.
Quantitative.
Quantitative. Grade. Grade A, B, C, D. Grade?
Qualitative.
Qualitative. Again, when you collect data, it will be a mixture of quantitative and qualitative. So describe, you need to know whether it's quantitative or is it qualitative. All right. First, we're going to see how to describe quantitative variables. Example, marks, distance traveled, BMI among students, okay, heights, weights, all these are quantitative variables. So to describe quantitative variables, we have measures of central tendency, meaning where is the data centered? right? Example, marks. Where is the mark centered? There are three measures to measure central tendency. We'll go through only the first two, not so much of the last one, right? We're going to go through number one and number two. Number one, mean. We use symbol X bar. Number two, median. We use symbol M. So X bar mean just arithmetic average. This median, the central value, the 50th percentile, right? An example, look at number one. Data 1, 2, 3, 4, 5. Where is it centered? Where's the data centered?
On 3.
Around 3?
Mm-hmm.
Right. Around 3, let's say we add the mean. How do you get 3? Add all the values.
Divided by 5.
Divided by 5. So that's called mean. As per definition, mean is the arithmetic average, sum, and divide. So some of the cases, 15.
Can you repeat, Doctor, how did you calculate it?
First, I'm talking about median. What's the median? Arithmetic average. So what do? Add all these values. Add all this. How much you get?
15.
15. 15 divided by 5. Why divide by 5?
Because there are 5 elements.
You added 5 values. So answer is 3. So when I say the mean is 3. Next, median. How do you find median? So clear off both sides. Take out this. Take out this either side. Let's see where the data is centered. But cancel this.
Is that is it like the middle of data points?
Middle. Right.
Yeah.
So where's the middle now? I slash one to the right, one to the left. That's the middle, right?
Mm.
I slash these two, and I slash these two. So the middle is 3. So in this example, mean is 3 and median also 3. Am I right?
Yes.
Yep.
All right. Next example. The data is 1, 2, 3, 4, and 5,000. So what's the mean? We add all these values, divide by 5 is 102. Is that right?
Yep.
Right. What's the median? Median again, is slash this side. Say slash this two
David. Come.
and slash this two. Is it still 3?
Yes.
Right.
Professor, what if there are even numbers? Like this is an example of odd numbers are present. So what
Okay.
if there are 4 numbers?
Yeah, I'll come back to that, okay? Currently, both are even numbers. So here, the mean is 3, median also 3. Over here, the mean is 102. So the median is 3. Hello? Yeah. Okay, right. Right here. Okay. Now, what's the difference between the two sets? Number one, number two, what's the difference?
The mean. It's
The mean and median are similar. What about here?
the mean is a lot more because of the outlier.
So what does it mean? How do you visualize this? This data is symmetrical. This data is asymmetrical, not symmetrical. So the purpose of studying mean and median, the mean and median are similar. Perhaps data is symmetrical. If the mean and median are very far apart, then the data is not symmetrical. Are you with me?
Yes.
What about others? Just a minute, hold on. Okay. Here, symmetry means what? There is a center point. If you cut here, you get equal halves. Whereas here, the mean is somewhere here, the median somewhere here. There's a huge difference between the mean and median. Therefore, data is not symmetrical. Are you following?
Yes.
Okay, give me an example where the data may not be symmetrical. Example, income. Is income symmetrical?
No.
Majority earn, let's say about 2,000. Very few people earn millions and billions. The data will be skewed. When I say look into the data, these are things you must look at, right? Later, all this you don't calculate. Some software click button things will come out. Right. Just now somebody asked, what if it is even number? Now what's the mean? What's the mean now? Come on, what's the mean? These are numbers I have. What's the mean?
2.5.
Okay, what's the total?
2.5, right? Mean.
Now what's the total? It's not total. What's the total here?
Oh, total is 10.
Divide by
4.
4.
Answer 2.5, right? Median. Median, let's say cut one to the left, cut one to the right. Now this center, right?
Mm-hmm.
So take the average of these two. So the median will be 2.5. Are you okay?
Yes.
Right. Don't bother, in our class, we use some software. So automatically, the median will be computed for you, but you must be able to understand what they mean. The mean and median are very close. You have data symmetrical. The mean and median are very far apart. Then we say data is not symmetrical. Right. Let's look at an example. Okay, look at this table. What's the mean value here? What's the mean value? You can see the table.
128.67.
Yeah.
128.67.
Right. What's the median?
129.50.
Are they very close?
Yeah, nearly.
Perhaps data is symmetrical.
Oh, okay.
Right? Let's see another example. What's the mean here? Class, are you following? What's the mean?
2.78.
3.718. What's the median? Median?
2.190.
It's close or far apart?
Yeah, yes.
Right.
This
Looks like, but we don't know, not sure yet. So we need other measures as well, like standard deviation. But mean and median are measures of central tendency, but these two alone not enough to describe the data. Right? So measure of central tendency, mean and median. We don't calculate manually in this class, click some button, answer will come out, we interpret. Next, measures of dispersion. Dispersion means what? What's the word dispersion means?
Like a distribution of data?
Distribution or how they're scattered, isn't it?
Yes.
Are they close, or far apart? Okay, in your hand, take your hand, one hand. Keep all the fingers very close. Spread the fingers. The fingers are very much together. Small dispersion, right?
Mm-hmm.
When you spread the fingers out, become very big spread, isn't it?
Mm-hmm.
So dispersion is a measure of the spread. There are so many measures here. First, we'll do the standard deviation. So click button, we get the mean and the standard deviation plus median. Okay. Next, how to get these values? Step by step are done how to get standard deviation. You don't have to know the formula or steps. In this class, no formulas. But this is how it is derived. By one click button, we know this value, right? In this example, what's the standard deviation value?
15.89.
0.89. So just we say the sample mean is 128.67 plus 15.89. That's all. This is where the data is centered, and this how much it is spread. Are we clear on this? Class, are you clear?
Yes.
Yes, sir.
Right. Let's say now we have another example. Okay, in this example, we have this. Let's say another example, another set of data. The sample mean was, how do you compare the first one with the second one? How do you compare these two?
So their standard deviations are different, right?
So how do you say in words? This is a measure of center, right?
Mhm.
Yes.
This is a measure of spread, right?
So the dispersion is not so big in the second one?
So we say center the same place, but the spread is bigger than this, right?
Yeah, so variations are less.
The variation or spread is higher. We visualize the data. One could be, when we visualize this, one could be something like this, wider spread. Second one is much narrower. So now we have same center, but different spread. Okay? Same center, but different spread. Are you following? Class?
Yes, yes.
Yes, sir.
Same center, but different spread. Okay, another one. If I take this, let's say for number 3. Number 3, this value is 28. So what's the difference number 2 and number 3? How do number 2 and 3 differ? What's the difference?
The sample size.
They're all same sample size. What's the difference between 2 and 3? What's the mean here? 1 to 8. What's the mean here?
28.
28. What is the standard deviation?
5. Both have the same standard deviation.
5. So
Yes.
what's the difference between 2 and 3?
The mean centers?
Centers differ. Center. So this is centered here. The third one, the center will be very much lower. Right? So number 1, number 2, same center somewhere, different spread. Number 2 and number 3, similar spread, right? But different centers. So these are very important. You know, compare between groups. They could differ in terms of spread, or they could differ in terms of the centers. So later when you go into testing of means, this all become very important to look into, right? By time being, we just want to know where the data is centered and how the data is spread. Now, taking these two, we go into skewness distribution. Look at the formula. Skewness is a measure of symmetry. Look at 3 figures below. Is the first one symmetrical? Symmetry means what?
Yes.
Symmetry means what?
Same on both sides.
when you cut along one axis, you get two equal halves, right?
Yes.
Is this symmetrical?
No,
Is this symmetrical?
no,
No.
No. Is this symmetrical?
yes.
Yes. So it's a measure of symmetry. I've given three different formulas. This is the exact
See,
method.
this is very difficult to understand, Doctor. Frankly speaking.
Right. You don't have to understand the formula. Look at the shape. The three graphs, the shapes. Describe the first graph. Describe the first graph. Is it symmetrical? Symmetry means what? The word symmetry means what? You cut, take an axis and cut here, you get two equal halves. What about here?
Normal distribute,
No, no, not yet.
not yet.
Not yet. Okay. What are symmetric objects? This object, is it symmetrical?
Yes,
Why?
because when you cut it, it will still have
I
a
can
mirror.
cut along one axis here. Are you getting similar halves?
Yes.
So we call it symmetrical. Another object. Is it symmetrical?
Yes.
Why?
Only if you cut it from the middle, and if you
Cut
cut it
here,
horizontally.
all right, that's symmetry. So it is still symmetrical, right? So this figure is still symmetrical because when you cut from that axis, you'll get equal halves. Right, cut here, you get equal halves. Am I right?
Yes,
Yes.
Class, am I right?
Yes. Yes, Professor.
Right, if you cut here,
No.
no.
No, not
means,
symmetrical.
There exists an axis along which you get two halves. Currently, is it symmetrical?
No.
This object, is it symmetrical? This object, is it symmetrical?
yes,
Yes,
You know, if I cut here, is it symmetrical?
No.
So there exists an axis, if I cut here, you get equal halves, right?
Yes.
So we say it's symmetrical. What about this? Is this symmetrical? You go and check. Does an exist, right? This axis, does it exist? Whereby you cut there, you get two equal halves. Another object. Is this symmetrical? Is this object symmetrical? This object, yeah? Come on, is it symmetrical?
Yes, yes.
So now, keep on moving. We come to one place. All right. You get two equal halves. So this figure is called symmetrical. I'll put in one more. Let's say I take this. Is this symmetrical?
nope.
Why not? Why not? You're going this way.
Because because it's not, the two is not equal of that ways. Yes,
But if I go this way,
yes, then it's
Right.
symmetrical.
Depends where you want to cut, right? So
Yes.
the figure is one, and how we cut, that makes a difference. Is it all symmetrical? Whether like this, like this, like this, still symmetrical, right? Let's go back
Yes.
to our figure here. Is it symmetrical? Number one.
Yes,
Number two?
nope,
No. Number three?
nope.
Right. So skewness just will tell you whether the data is distributed symmetrically or not. There are three formulas here. Look at the formula we have highlighted here. Look at the numerator. What's the numerator in the formula? What is the numerator? What's X bar?
mean,
D. What's M?
median, I guess.
Yeah. right? Your X bar is a mean, M is your median. So this formula, if X bar equals to median, what is skewness value? Class, this is a formula for measuring.
0.
What is the formula for skewness? The X bar and M are equal. What is the whole value?
0.
Symmetrical.
0,
Yes.
right? 0 means it will be symmetrical. When these two are equal, this value is 0. So just now I said, you look at median and mean. If they are similar, then data is symmetrical. What is X bar is very much bigger than M. And let's say X bar is 100, M is 20. Is it very positive?
Yes.
Right, we still don't know yet. We must look at the standard deviation. Right? Let me give an example. Let's say now, mean equals to 20, median equals to 18, standard deviation equals to 5. What is skewness value now? Just use this formula. What is skewness value? 20 minus 18
1.
divided by 5.
1.2.
1 point?
No, just 5.
Calculate what's the value?
Yeah, 1.2. Right.
1.2.
No, it will be 0 something.
20 minus 18 is 2. Oh, sorry. 2 divided by 5 times 3. What's the answer again?
6 by 5.
One
1.
divided 5.
1.5.
Yes, it's
Right. So this alone, 2018 not alone, not enough. We need standard deviation. So what is standard deviation?
1.2 actually.
1.2 is it?
Yes.
Okay, 1.2. So the mean and median, are they close or far apart?
Close.
They're close.
Looks close. But the standard deviation also counting. Standard deviation comes in. So this 2 divided by 5 times 3. Is it correct, 1.2?
Yes.
Right.
yes.
Now let's say now, this is 1. What's the skewness value?
2.
Right? So there's 2 or 6.
6.
6. Sorry. Yeah, 6. Sorry,
20
sir.
minus 18 is 2 times 3 is 6. So now the skewness depends on the S value as well, right?
Yes.
Not just the mean and median alone. It depends on the S value as well. So now you know why you must study mean, median, and standard deviation. Because you want to see a distribution. Does it look like number 1, number 2, or number 3? So now, general guideline, look here, generally, skewness value within plus or minus 1, we can assume symmetry. Skewness value within plus or minus 1, we can assume symmetry. Now, is data symmetrical? Is this data symmetrical?
No, sir.
Why?
Greater than.
Why?
And the median supposed to be equal, then it's symmetrical.
Not necessarily equal. I'm giving guideline here.
The
Within
skewness
plus
is
or minus 1.
Because it's more than 1.
Very more than 1. So data is not symmetrical. If this is 10, what is skewness value now? Come on, calculate.
0.6, sir. 0.6.
Is it symmetrical?
yes.
Yes.
Is it within plus or minus 1?
Yes.
Right. So we take value from minus 1 2 plus 1. If the skewness value is inside here, you can imagine it is like this, symmetrical. If the skewness value more than 1, this is 5, 1.2, more than 1, then data is like number 2, skewed to the right. Supposing this value is 20, this is 22. So what is skewness now?
Negative 1.2.
Negative 1.2. Is it outside minus 1?
Yes.
Therefore, data is
Not symmetrical. Negatively skewed.
Negatively skewed. Now, anyone still confused? You don't have to calculate manually. Click button, answer will come. You interpret. Are we okay?
Yes.
Come on, are you all okay?
Yes.
Yes, Prof.
In my example just now, did I calculate manually? Is the value there already? Is the skewness value there?
Yes.
What's the value?
0.271.
Is it within plus or minus 1?
Yes.
What's the conclusion?
Symmetrical.
Symmetrical. Right? It computes for you automatically. Another example. What's the skewness value here?
1.915.
1.915. Is it more than 1?
Yes.
Therefore, data is not symmetrical. It is skewed to the right. So when you do analysis, when somebody said, look into your data, tell me about your data. These are some of the things you look into. Where is the mean? That means where it's centered. How's the spread? How's the standard deviation? Where's the median? So what does it mean? How's the data distribution? Is it symmetrical or asymmetrical? Right? So this example now, this might mean this is a median, 2.19. How do you interpret the median 2.19? Zach, can you mute? Right. Right. How do you interpret this median value? How do you interpret the median? At least 50% for the participants TG is more than 2.19. The median is the center 50%. Skewness more than 1. Data is 2 to the right. So these three are the main points. Okay, small better mute, okay? Somebody having class within class. Who's talking?
Menu.
All right. Okay. Now you've gone through the center. We're talking about how the data spread and where it's centered. Number 1 is a measure of center, mean and median. Number 2, measure of dispersion. And number 3 is measure of symmetry. Right? Next, we go into identifying whether there are major, extreme, or outliers. Extreme or outliers. We use a box plot. So what does a box plot do? It partitions the data into 4 quarters. From here to here, 1 quarter. Here, another 25%. The middle, the box contains 50%. The center line is called a median. So the end line here, the end of the box, is called the first quartile. This is called the third quartile. Why is it called first quartile? 25% of the cases are below this point. Third quartile, another 25% are above this box length. Inside the box, 50% of the cases are here. And the median is the center, right? So we look for these kind of diagrams and see any asterisk signs or circles beyond the whiskers. These are called the whiskers, whether above or below. There are no asterisk signs, no circles, then we conclude there are no outliers or extreme values. Let's look at the example. Okay, look at the example here. This is a box plot for one variable. Are there any circles beyond this whisker?
No, sir.
No. Are there any asterisk signs?
Nope.
That are above?
What's a box plot, doctor?
It's a box plot. Later, when you do SPSS, we ask for the box plot. SPSS produce the box plot. What's the use of box plot? The box plot will indicate whether any extreme values are outliers. Look at the second diagram. What do you see now? This is a box, this is a whisker. Are there asterisk signs?
Yes.
Are they outliers?
Yes.
Circle indicate outlier. The asterisk sign indicate extreme values. So in this data set, there are several outliers and several extreme values. One of the purpose of box plot is to determine if there are any outliers or extreme values. Again, compare these two diagrams. Are there any outliers?
No.
Are there any asterisk signs here?
No, sir.
No. What about here?
Yes, it has.
There are some extreme values and some outliers. So this helps to visualize the data and do some diagnostics to see any outliers or extreme values. Now, this is very important. If the data is something like this, we may be able to use parametric test. Data comes like this, we may have to use non-parametric test. This all helps you to visualize the data, right? So now we have gone through number 1, number 2, number 3, and number 4. What's the mean? So where do you get it from? From this table. What's the mean? What's the median, and what does it mean here? And what's the skewness? Next, from the box plot, are there any outliers or asterisk signs? None. So we conclude there are no outliers or extreme values. The last one is normality. Is the data distributed normal? Okay. Right. Normality, the data to be normal, there must be few conditions met. First condition, it must be symmetrical. Is this diagram symmetrical?
Yes.
Yes. It must be bell-shaped. Is it bell-shaped?
Yes.
Is this diagram bell-shaped? Example. This figure, is it symmetrical?
Yes.
Is it bell-shaped?
No.
Then cannot be normal. A box, is it symmetrical?
Yes.
Is it bell shape?
No.
Yes.
Is it bell shape? Is it bell shape? Bell? Have you seen bell?
Yes, but this
Yes,
is
yes.
mentioned.
Is it bell shape?
Yes.
Huh?
Yes.
No.
Yes.
No.
The bell means you tie something in the middle, then we turn to the left and right to make some noise, isn't it? That's a bell, right? Isn't it? We hang something circular object and bangs left, right, left, right. This got a bell shape. But this is not a bell shape, right?
No.
No. Next, this diagram. Is it symmetrical?
Yes.
Yes.
Is it bell shape?
No.
Yes.
Yes, sir. But
No.
this is bell, like a bell. You tie up something here. You understand what
Alright.
bell?
The circle is not a bell, right?
Say again.
The circle is not the bell, right?
All these structures, they are symmetrical,
But
but
they're not bell shaped.
they are bell shaped.
If it is in diagram, yes.
Say again.
If it is in diagram, I think it will be well shaped.
Bell shaped.
It's not in the diagram, it's for example purpose.
This is
That's-
circle. It's not a bell shape. It's rectangular, not a bell shape. It's triangular, not a bell shape. Bell shape means what? There must be a curve. There must be a curve to the left and to the right.
Oh, yes.
These are not bell shaped. So what's the lesson learned? Symmetry, not necessarily normal. Isn't it?
Yes.
Distribution may be symmetrical, but not necessarily normal. So first condition met, second condition not, so all this not normal. The graph must be bell-shaped. Still not enough. We partition the area under the curve by means and standard deviation. The mu is a mean. It's a mean. Sigma is a standard deviation. We partition the whole curve. This is mean plus or minus 1 standard deviation between the green lines. Mean plus or minus 1 standard deviation. The area under the curve must be about 68%. The area under this curve here must be roughly 68%. Still not enough. If we partition within plus or minus 2 standard deviations, the area must be at least about 95%. Still not enough. Partition the area within plus or minus 3 standard deviations, almost 100%. Then we have a normal distribution. So if I ask you, what's the characteristics of normal distribution? Number one, it must be symmetrical. Number two, must be bell-shaped. Number three, the area under the curve, mean plus or minus 1 standard deviation must be this, 2 standard deviations must be this, 3 standard deviations must be this. Then we call it a normal distribution. Without this, we can't call it normal. Looks normal, but may or may not be normal, right? So what does it mean here? What's the application? Look at this now. Exam in marks, sorry, marks in exam. Let's say I know the marks are distributed. When I write this way, X indicate marks, the curl indicates distributed, normal, this is a mean, this is standard deviation, right? So how do you say in words? The marks are distributed normally with a mean of 50 and a standard deviation is 5. Just one expression contains so much of information, right? So marks, distributed, normal, with a mean of 50 and standard deviation of 5. So what does it mean? Where's the center? 50, right? Class,
Yes, sir.
okay, right? 50.
Yes.
Now, plus or minus 1 standard deviation. So now we go plus or minus 1 standard deviation between 45 and 55, right?
55.
Yes.
So how much this area? At least or about 68% of the students' marks must be between 45 and 55. About 68% of the students' marks must be between 45 to 55. So we got 2 standard deviations between 40 and 60. So what does it mean?
95% of the student earn between 40 to 60 points.
So 95% of the students' marks will be between 40 to 60. Plus or minus 3 standard deviations. So what does it mean here?
Almost 100% of the student marks
Yeah.
between 35 to 65.
Right? So this normal distribution is heavily used in almost all industries. In almost all industries. Medical, heavily used. Manufacturing, agriculture, name it. Almost all sectors do use this particular distribution. Therefore, you must looking at the data is very, very important. Right? What's the normal temperature? Normal body temperature? Now, before this, what are the chances of the value being 60? What are chances based on this? Chances value being 60? 60 is here, right?
95%.
Right, roughly. What about chances of 80? To get A, you must get 80 and above. What are chances of you getting A? What are chances of you getting A?
No chance.
Why?
No chance.
80 is sitting somewhere here, right?
Yes.
Almost all of you will get 35 to 65. 80 almost nil. So with this ask you question, what are chance of getting A? To get A must get 18 above. Your chances are almost nil. All the values are derived from this normal distribution table. So you don't have to go in detail, but you must be able to, from the output, recognize if the data is distributed normal. For this, in our analysis, again, click button, we'll get some output. In this output, the SIG are called the p-values. SIG are called the p-values. There are 2 tests given, Kolmogorov-Smirnov, Shapiro-Wilks. When the sample size is large, more than 50, the sample size is more than 50, use Kolmogorov-Smirnov, KS. If the sample size is less than 50, use SW, Shapiro-Wilks. Right? The DF is the sample size. So in this case, which test to use, Kolmogorov-Smirnov or Shapiro-Wilks? But the sample size, the DF is sample size, in this case, is more than 50, use Homographs you know.
Yeah.
In this case, which test you will use?
Yes.
The case.
KS. Why? The DF is more than 50, 108. So yours, this p-value, is it more than or less than 0.05?
More than 0.05.
So listen carefully. If this value is more than 0.05, we can say the data can be assumed to be normal, distributed normal. If the p-value is more than 0.05, we can say the data can be distributed, can be assumed to be distributed normal. What about now? What about now?
Less than
Less
0.05.
Less than
Oh.
0.05. Less.
Therefore,
It is not normal.
Not normal.
so less than 0.05, we say data is not normal. Data is not. That's all. Again, if the p-value is more than 0.05, we say data can be assumed to be distributed normal. Right, this part. If the p-value is less than 0.05, then is say less than 0.05, then is say data is not distributed normal. Right? Right. Normal means what? It must be symmetrical. It must be bell-shaped, and the area under the curve from 130 plus or minus must cover this area. Right? The person says my data distributed normal. Number one, it means symmetrical. Number two, bell-shaped. And based on the mean and standard deviation, we can imagine what are the cut points. So this assumption is very, very important for most analysis. So you must know how to recognize this. Now I complete the 5 points. My mean and standard deviation, median and what it means, skewness, what does it mean, and the box plot, what is telling us, and the p-value, what is telling us. So with this 5-point summary, you can moralize, visualize your data. Very clear? So
Yes, sir.
Normal means what?
Okay.
Normal means what?
Symmetrical.
Symmetrical. Symmetrical means what? The skewness must be within plus or minus 1, right?
Yes.
And also the mean and median must be close, right?
Mm-hmm.
Right,
Yes.
symmetrical. Next must be bell-shaped and follow the cut points for the area under the curve, right? And box plot, it tells you whether any values which are outliers extreme. Look at the second example. Right. So that's a mean, that's a median, that is skewness. So report here. That's my mean, that's a median, that is skewness. So what does it mean here? Is it more than one skewness? Is it more than one?
Yes.
That means data is not symmetrical, right?
Yes.
Data is skewed. That means the 2.781 is not close to this value. They're far apart. If the data is skewed, can it be normal?
Not necessary.
No. Skewness not necessarily normal, but normal must be symmetrical, right? So data is not symmetrical, then definitely it's not normal. If the data is not symmetrical, then it cannot be normal. Normal data must be symmetrical. If it's not symmetrical, then cannot be normal. Are you okay?
Okay.
Because it must be symmetrical, must be bell-shaped before it can be normal. If it's not symmetrical, it cannot be normal. Why it's not symmetrical? Why is it not symmetrical? Look at this diagram here. Because they are outliers and extreme values. Look at the histogram. Can you see histogram? Peak here and skew to the right. So what's the p-value in the test of normality? When SPS reports 0.000, you report this way, less than 0.001. Is this figure less than 0.05?
It's less than 0.05.
Therefore,
Therefore, it's not
it's
distributed
not.
normal.
So the 5-point summary, we've seen median, mean, skewness, and the box plot. So this is a case number 3470108, asterisk signs. So these values are about between 8 and 10, about 9. These numbers, these are case numbers, are about 7 something, right? So we know this was happening. So because of this, the data will be skewed to the right. Ultimately, the data is not normal. Are we clear?
Yes, Prof.
Right. Now, I'm going to show some output because some of you don't have the space working. You're going to give me the 5 points, right? Let me open the data, one set of data.
Which data should we open, Professor?
Just hold on, because some of you don't have the data. I'm going to do the analysis, you interpret, okay? Are you okay?
Yes, sir.
I do the analysis. I'm going to do it now. Analyze data and get the SPSS, you do it, right? Descriptive, explore. So in your notes, I've given this procedure. In your notes, how to do it. Okay, here. For this data, this is how you do it, right? Follow this instruction. Okay, let's do it. Somebody tell me what to do. Read this and tell me what to do. Anyone? Guide me what to do.
Yes, sir. I'm okay.
Okay, tell.
So you need to go to the menu and choose Analyze.
The menu, choose Analyze, okay?
And then you need to go down to
Descriptive,
Descriptive
statistic,
statistics,
and then explore.
and then explore. Is it difficult?
No, not
You
yet.
follow whatever in the yellow box, just follow.
Yeah, not yet.
Now what it says? Now what must you do? For which variable, right? Variable
Yes.
BMI. So that variable BMI, we want to explore the variable BMI. Next, what do you do? Follow the diagram, what do you do? In the notes?
Plots.
Plots. In plots, what do you click? What is center here?
Normality.
Normality plot with test. Right? You want histogram, you can click the histogram. Box plot is already there, click for you. Again, let's start all over again. Somebody guide me from beginning.
Analyze.
Hold on, now somebody's waiting. On accessing. Okay. Okay, tell me.
Analyze.
Analyze,
Descriptive statistics.
descriptive statistics,
Explore.
explore. Exactly what's given in the notes. Okay, next. Explore which variable. So what's the variable here?
BMI.
BMI SBP.
No, sorry, here SBP.
SBP. So search for SBP. That's a variable. Click in. SBP. Next. Next.
Box.
Plots. Click what?
Normality.
Normality plot. One histogram. Box plot already clicked for you. Continue. And click OK. Okay, going to go through the 5-point summary. All right. First point. Mean 128.67. Standard deviation 15.889. Is that okay? Class, is it okay?
Yes, Prof.
Right. Next,
Yes, sir.
median. What's the median value? Median
129.50.
9.5. Sorry there. So it's not enough just to mention that. So what does it mean? At least 50% of the participants' BP is more than 1 to 9. Next, skewness. What is skewness value?
0.271.
271. 0.271. Is it within plus or minus 1?
Yes.
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 Less
What
than
does it
1.
mean? What does it mean? I can put there,
Data symmetrical.
I can put there less than 1. That means close to 0. That means data can be assumed to be symmetrical. Next, box plot. What is seen in the box plot? Any
No
extreme-
outliers and no extreme value.
outliers.
No extremes, no outliers.
Next one. Test of normality. Test of normality. Which test is used? Homography or separables?
KS.
KS. So what's the p-value there?
0.061.
Is it more than or less than 0.05?
More.
More than 0.05. Therefore, data can be assumed to be distributed normally. Any questions? Any calculations?
Prof,
Any
just is there a difference between the outliers and extremes, or all they
Yes,
are
yes.
they similar?
Okay, what's the different outliers next week? We follow this. Outliers still may belong to this population. Box plot, eh? Okay. These outliers may still belong to this population. Extreme values, they are outside this population. If I go and check, there's a possibility of typo. Example, let's say blood pressure. Instead of a 159, you type there 1159. There's a typo, isn't it? It'll show. You go and check the data. Right? Birth weight, newborn baby's birth weight. Suppose a value 12. Is it possible birth weight 12? Newborn baby's birth weight 12, is it possible? Eh? Newborn baby's birth weight 12 kg, is it possible?
No.
I don't think.
Elephant's daughters can, right?
Yes.
The birth weight 12 kg, is it possible or not?
No.
That's a world record, okay, so far. But it's not very common. Not very common. Maybe 2.5 kg is a typo. You type there 12.5 kg. Possible?
Possible.
Go and check the data. If it is there, no mistake, it is there, we remove it. We remove that from the analysis. because that's not very common. Are we clear? Circle can still be part of this population. Example, birth weight 5 kg. Is it possible? Birth weight 5 kg?
Yes,
The
possible.
higher side, but not right extremely far from the others. Very rare, that's possible. So outliers I can still keep in the study. Continue with the outliers, but not the extreme values. Is it okay?
Yes, yes.
Now I'm going to show the second example. Triglyceride. Okay, tell me how to do it. What are the steps? What must I do? Okay, whatever I did just now, same thing, right?
Analyze.
Analyze.
Descriptive statistics.
How come others not participating?
Explore.
Explore. Which variable?
SBP.
SBP. No, next one.
Oh, next.
Triglyceride. TG.
TG.
Plots. Histogram. Normality plot. Continue. Click OK. So what's the mean? Mean
2.780.
right. Okay. 2.781. Standard deviation 1.75. Median. So what's the median value? 2.19. It means this. Skewness. What is skewness value? 1.915, which is more than 1. Data skewed to the right. Box plot. So box plot. How many of them? How many cases here? These are case numbers. How many cases?
3.
3 cases. Case number 34, 70, 106. Approximately, what's the value here? Project to this. What's the value?
9.
9. TG, cholesterol 9. Is it common? Science students, cholesterol 9. Is it common?
No,
Right?
no, because it's an extreme value.
Extreme value, you decide. But medically, people say it's possible, then you can't throw it. Then you must do some other methods of analysis. Now these circles are called outliers. You go out from this box here, not too far from here. How many of them? How many of them here? Yeah?
6.
6.
6.
The cases, these cases. What's the value? Project onto this axis. Are they between 6 to 8?
Yes.
Right, they are between 6 to 8. Normality. What's the p-value for normality? So what's the p-value?
0.
Now, especially you don't say 0. You say less than 0.001. Right? Is it less than 0.05?
Yes.
Therefore, data is not distributed normal. Are we clear?
Yes.
Right. I'm going to do one more example. You do the write-up.
Hello, Professor.
Yeah?
I have some questions,
Yeah, okay.
which just you teach us some parts I don't understand.
Which
Can
one?
I ask?
Yeah, sure.
First of all, TGSBP, what is represent? What does this mean for these two?
TG? TG is
Yes, what's mean
triglyceride.
Pardon?
TG is triglyceride. TG.
Can you help me to type TG? Can you help me to tell?
Those are variables. We don't need to worry.
Okay, TG, like cholesterol, LDL, HDL, right? Look at this one, the TG, triglyceride. Very good. Right? See, triglyceride. You know the cholesterol in the blood?
SBP?
SBP is systolic blood pressure. Blood pressure.
Oh, okay.
Diastolic blood
Okay.
pressure. All right? These are variables.
Oh, okay.
All right.
Besides just your teachers some part, I don't understand, not so understand about the box plot, the
You don't
extreme
understand
and
box plot.
outliers, what that represent mean.
Okay, box plot. Let's look at the example triglyceride. Okay.
Prof, sorry.
Ah.
Yeah, it's Dave here. Just want to ask because I want to know the definition for like outliers and also the extreme values.
Okay.
What do they represent? Yeah.
How they're defined, right?
Yes, yes.
So look at the diagram again. How the outliers and extreme values are determined. Right. So what is an outlier? Values more than 1.5 box length from Q3. So this is a box length. Are you okay? Box, which is a box? This is a box, right?
Yes.
So box length refers to distance from Q1 to Q3. Q1 to Q3, also known as interquartile range. Interquartile range. So what's interquartile range?
Okay.
The distance between upper and lower quartiles, right? Supposing this distance is from here to here is 5. From here to here is 5. How far away a point is considered outlier? Now, what's the definition?
Right.
More than 1.5 box length, isn't it? From Q3, right? This is 5. If this is 5,
yes.
How much 1.5 times 1.5?
7.5.
7.5.
7.5 from Q3.
Q3.
Right? More than 1.5
Yes.
box length from Q3. So from here, go up 7.5. All those more than 7.5, outlier. Are you okay?
Okay.
Now, what's the extreme value? 3 times box length. 3 times box length from Q3. If this is 5, 3 times 5, 15, right?
Yes.
So 15 from here up, anything more than 15, that's extreme value.
Okay.
That's how they are they're computed within. In our example, remove all this. Okay. What's the box length? In our example, what's the box length? I mean, from here to here, what's the box length?
1 point something.
That's your interquartile range.
Quartile 1.66.
1.6.
1.66.
That's the interquartile range, 1.66. Times 3?
Okay.
Times 3, how much? 1.6
Times 3.
Times 3?
1.
Roughly?
4 point something.
6.
More than 6?
4 point something.
5 to 6.
Right. That means from here all the way up
6
here.
plus.
Right? So this value here roughly how much? About 3? Can I say about 3? 3 point something?
3.5.
This lower quartile is about 1 point something, about 3.5. So 3.5 plus 6 all the way up here. Are you okay? I'll show here. So what's the interquartile range for second one? Interquartile range, how much? 1 point?
1.66.
1.66
times 3?
Yeah.
1
times 3.
Times 3? How much?
4.98.
4.98.
98.
4.98. That means from here goes up. Anything more than 4.98 considered extreme value. Right? 1.5 box length. 1.5 times this. How much?
1.5 times 3.
Times this value.
4.5.
1.5?
Times 3, right? 1.5.
No.
2.49.
So for the extreme value times 3.
Yeah.
Outlier
Outlier is 1.5. Yeah. 1.66 times 1.5. 2.49. Maybe 2.5.
Here you go up. So these are outliers, right? Okay. Above this are outliers. Go 3 times above this, they are extreme values. Okay? But you don't have to go to that level of interpretation. Just say, as seen in the box plot, there are 3 extreme values, right? 3 extreme values in these cases with values about 9. And there are 6 outliers in these cases with the values ranging from here to here. You don't have to mention the box length times 3 times 1.5, no need. Right? This is for you to visualize and interpret. Right?
Okay.
Are you okay? All right.
So basically, the box plot to tell us like, I mean, how many outliers and how many extreme values. That's
Right.
it.
So what should be done? It can be a typo, right? Instead of 1.9, you type the 9.1. Also possible, isn't it? Typing could have made a mistake, right?
Yeah.
Yes.
Then go and check which case number, right? They show the case number, which number. Show an example. So just now,
So you go to 34.
okay.
Okay.
Age. Instead of 33, externally type 333. So I do the test now. Do the analysis now.
Okay.
Right. This is for age. Okay. Look at the box.
It's a bit different. Yeah. So.
Okay, how come a person has 300 something age? Right?
Oh, okay. Understood.
I go and check. Oh, this is a typo. 33. And then
Okay.
Check again. Right. Now, okay, right?
So this is not wrong. Okay.
Also a form of diagnostics. But just now I know it's here. It can be anywhere, right? It can be anywhere. I don't know where.
Yeah.
That's the test now. This will tell you which case. Case number 75. So go to case number 75. 74, is it?
74. So we go to 74 and check the thing. Oh, okay. Understood. So
Right? Yeah, thank you.
So data checking.
So that means.
Yeah.
So that is the function of using the box plot. Just to
right, one function.
Check that.
Data cleaning.
Okay. Okay, data screening.
Yeah.
Okay, good.
Any other questions?
So.
Yeah.
Very clear.
So Professor, that is mean if we have outlier or extremes, that means it's normal, right?
Definitely.
So if within the box plot, that means
no. Box plot only tells you identify whether outlier is extreme. Does not test for normality. Normality only this test only will tell whether normal or not. Okay.
And okay, Professor, and for the test of normality, this part I'm also not so understand what its p-values means.
Next class we see that. Time being, the next class we see that. Okay. Time being, see whether it's more than or less than 0.05. That's all. Is it more than 0.05?
Okay.
Is it more than 0.05?
Yeah. Yes.
Yes. Then you see data can be assumed normal.
Not distributed normal.
No, is distributed. In this case, 0.061,
No, normal.
more than 0.05. Therefore, data is distributed normal.
So prof, normally p-value tells us like whether the data is distributed normal or not normal, right?
Okay, now you see, my question is the data distributed normal, isn't it? Is the data distributed normal? I look at that p-value, the one in circle. Is it more than or less than 0.05? If it is more than 0.05, we say yes. Less than 0.05, we say no.
I see.
My question is again, is the data distributed normal? So look at the figure, circle is red. Is it more than or less than 0.05? If it's more than 0.05, we say yes, data is distributed normal. Less than 0.05, we say data is not distributed normal. That's all right, time being.
Yeah. Okay.
Questions?
Okay, thank you, Professor.
Okay. So I give one more example. You write the report for me, the 5-point summary. Okay, BMI. Okay, BMI. You're supposed to write the 5-point summary like this.
Based on which data?
No, already done. I'll show you because some cannot do.
Okay.
So I'll show you.
All right.
So I show you the output from where you must interpret. Okay, with this.
Oh, okay. Just copy the table.
Yeah, I'll give the table, you interpret.
Oh, okay. That's it.
One table. It's another table. And that's the diagram. So giving this based on the output, you're supposed to interpret or write the 5-point summary. You know what I'm supposed to do? You're supposed to write this 5-point summary. Take a piece of paper and write. Okay. Right, go ahead. All the values required is all shown there.
We give you the feedback now.
Yeah, write it now. Write it now. Take a piece of paper, write it now.
Okay.
Write it exactly like this 5-point summary. Okay, give me feedback now.
Mean is 28.4.
28.4.
Yes. Median is 28.
What about standard deviation? You can't say mean.
5.24.
Oh, yeah. Plus point.
Plus minus.
Plus 5.24.
5 point.
5.24.
Okay. Median.
It's
28.
28.
28. What does it mean? Participants BMI is more than 28.
28%.
Right. Skewness.
Negative 1.27.
Negative 1.27.
Data is negatively skewed.
Which is?
Greater than negative 7.
No, less
Sorry,
than.
greater than negative 1. Sorry.
Less than -1.
Yeah,
Less
not
than.
distributed, not symmetrical.
Yeah.
Less than
Non symmetrical.
Data is not symmetrical. Or I can say data is skewed to the left.
Non-symmetrical. It's not distributed normally.
Skewed to the left. Right? You can say this. Skewed means no more normal. In the box plot, what did you see?
No outliers and all extreme values.
All right. That's a normality.
No, not normal.
What's the p-value?
0.02.
0.02. Yes? Is it less than or more than 0.05?
Less than.
Less than. Therefore, data is it normal?
It's not normalized.
Not. Yeah. Once the data is skewed, it cannot be normal, right?
Yep.
Questions? Okay, one more example. Okay, that's great. Right, weight variable. Okay, so weight. All right. Okay. The answers? Ankita?
7.
Ankita? Azaber?
Yes, Professor. Mean is 76.375.
77 point?
375.
375. Okay.
1.200.
Can't hear. Yeah?
15.2.
15.2. Okay. Median?
76.650.
5. Okay. What does it mean?
It means at least 50% of the participants have a height of weight.
Weight.
More than
Then?
76.
Yeah.
More than 76.65.
Skewness?
Skewness is
Skewness?
0.2.
7.
Negative? No.
0.72.
Negative?
Negative 0.03.
0.03. Okay, 0.03. Okay. Which is?
Plus minus 1.
It is within, you can say within.
Within, yes. Within 1. So it's symmetrical.
Right. Within minus 1. For data is?
Symmetrical.
Symmetrical. Box plot. Box plot.
Value.
Box plot. What is in the box plot?
No.
No? Outliers, extreme values.
No outliers. Yes.
P value for normality.
P value 0.2.
Right? 0.200. Okay. More than?
Greater than 0.2.
What data is?
Distribute.
Normal.
Right? Distributed normal.
Normal.
Right.
Normal.
So descriptive, more or less, that's all you are supposed to know, how to describe the data.
Prof.
Yeah.
Prof, can you please show the slide 30? Yeah, thank you. And just want to ask you, right, regarding the box plot, right, we can only check whether they are outliers or extreme values based on the box plot given in the the graph, right? Cannot. I mean, it cannot tell based on the table given, right?
No, cannot tell from here.
I see. Okay.
Of course, you can calculate, but I can't see individual value. Summarize value, right? Here, this is individual values. I can see whether outside or not, right?
I see.
So I still
all right.
Plot.
Okay. Thank you.
Okay. Now, this is for quantitative variables. For qualitative variables, very straightforward. Right? So this is for qualitative variables. Example, gender, job category, marital status, all these are qualitative variables. So qualitative variables, we use, right? We follow these steps. Okay. Now I'm going to do it. Somebody guide me. I'm going to do for which variable? Category, job category. Okay, somebody tell me what am I supposed to do? Somebody direct me what to do? Analyze.
Descriptive statistics.
Descriptive statistics.
Frequencies.
Right. Frequency for qualitative variables. Explore for quantitative variables. That's it. All right. Which variable?
Category.
Category. Job category. That's all.
Doctor, how are you?
Okay.
Doctor, I think these things that do we need to understand it in details, or just we send our data to the computer, then one click, everything is okay?
You must understand the data. Computer doesn't know anything. You must understand what you are analyzing. All right? You must understand your data. This SPSS, whatever software, only just to help you. That's all.
Yeah, doctor, what do you advise student from not statistical background to do?
Basically, what I'm doing is for non-statistical background. Because I'm not teaching any formula. It's only how to use it, interpret, and finish off whatever project or thesis. Right? But you must understand, otherwise cannot write. Example, skewness is negative 4.5. What does it mean? Negative 4.5, very much lesser than -1. That means we know the data is heavily skewed to the left. Then what do? Right? So that understanding must be there.
Yes, doctor, yes.
We're not asking to measure, we're not asking to calculate manually, but the value comes out. Let's say now your, let's say your median, say median pressure is 150. What does it mean? At least 50% of the people or respondents, PP is more than 150. It's only able to communicate, we understand better, right? Okay, job category. I click OK. So look at the results. Very straightforward. How to interpret this now? What are the three groups of workers there? Attendant, nurse, and doctor. How many attendants? How many attendants?
33.
33.
33.
How many percent?
30.6.
30.6%, 33.3%, 36%. Now, there are two columns here, percent, valid percent. Are the values exactly the same?
Yes.
Why are they giving two columns value exactly the same?
Because the mean and median are the
They got mean and median. Mean and median only for quantitative variables.
Because two parameters, nurse and doctors.
Let me do one more. For marital status. Are these two columns exactly the same?
No.
No.
So what's the difference now? Here same, right?
Yeah.
Here different, right?
Yes.
This is called valid, meaning in this column here, there are 6 missing, isn't it? That means 6 people did not disclose.
Misclustering.
Did not disclose.
Doctor, is it the same meaning of misclustering?
No, it's not misclustering. That's different. So look at this person. Look at the data case number 10. This person did not, right, tell his marital status.
Data.
So
we say, he didn't say anything. Can I simply put married?
Cannot.
Cannot. So we don't know. When you don't know,
the data is not valid.
Not valid. We leave it blank.
Okay.
We can't make any judgment for it, right? So now, what do you say now? Out of the 102, 8 did not disclose the marital status.
Okay.
Out of the 102, 26.5% are single. 61.8% are married. 7.8% are once married. Out of the 102, right? This also relevant. How many percent are missing? 5.6%. Right? Sometimes we also look at it now. The percentage missing, is it very high? Supposing this 50.6% are missing. What does it mean? 50.6% missing means what?
It's not reliable.
Half of them did not disclose, right?
Yeah.
That variable is not good for analysis.
Okay.
Okay, how big? Some say more than 10% is not good, right? So this is 9.6%. If we say, okay, go ahead, right? If this is 19.3%, then we say, oh, there's too many missing. Either data collection is poor, or people did not understand the question, or very sensitive question, people don't answer, right? So whenever there are missing values, we refer to the valid percent. Right. So not necessary. You must do one by one. You can put all the qualitative variables together. So these are called demographics, right? Demographic variables are bring and do one shot. So now we have distributions of gender, job category, and marital. So I'll fill up in this table too. So in here, chapter 4, demographic characteristics of the respondents, you must show this in the first table. Don't show one table for each variable. All the demographics show in a single table. Look at this table. I categorize, I break into two, frequency and percentage for qualitative variables. That's for qualitative variables. Means and standard deviation for quantitative variables, like age. All the demography are shown in one table. Are we clear? Right.
Yes, Prof.
So now all the values here will be transferred inside here. Now come to marital status. Right? Marital status. What's number one? Single, married.
Single, married, one's married.
And one. So these numbers here, what will be number here? Go to use number 27.
27, 63.
Percentage is here?
25.
No.
26.5.
26.5. Because there will be some missing values.
Oh, I see.
Right. Next one. 63.
12.
63 is much. 61.8%. And the last one, 12. How many percent?
11.
Percent.
11.8.
So when you add this up, you won't get 108, right? You will get 102. So this addition, 51, 57, will be different from here. So when you look at this, we know there must be some missing values. On the other side, means. So now we have, let's say now, I go back to age variable. Okay. Okay. Right. So I go to age variable. Age variable, I'm going to explore because quantitative. Age variable. Right. This will mean 41.56 plus or minus 5 point. The value may be slightly different, doesn't matter. 5.41. Now here using mean and standard deviation because the data is symmetrical, isn't it? Are you okay?
Yes, yes.
Right. If the data is not symmetrical, example, just now your triglyceride, TG. Is the data symmetrical?
No.
Then we know data is skewed. It's better not described by mean and standard deviation. Should rather go by median, center, better representation. Median and your interquartile range, 1.66. When somebody writes this, we know this variable TG is under the column of mean, but put a strict sign, put a footnote, okay, sorry. Put a footnote there. Look here, this is not mean, but median. Are you following this?
Yes.
All right. Then, yeah. So this is median and interquartile range. It's not mean. Still under the column of mean, I can't be opening up one more column for median. So I put an asterisk sign and I put a footnote that is IQR, interquartile range. So remember, the data symmetrical, you can use mean and standard deviation. The data is skewed, so rather use median and interquartile range. So one table will be for the whole demographics. Are we clear on this?
Yes.
Professor, can you please explain once for the frequency, that is qualitative data, because sometimes we were referring to percent, the column where percent was written, and the other times we were referring to valid percent something.
Now about this.
Yeah.
Table for female, male, the percent, valid percent are same values, right?
Yes.
So you wonder why they give two tables, right? Two columns, right?
Yeah.
But here, job category also same. But come to marital status now, these are different, right?
Yes.
So this percent, 27 over 102. 102 are the known values. Okay. 27 over 102. 27 over 102 is 26.65. If I take 27 over the total, this 25. Now, which is more reasonable? To say 25% are single or 2.6, 25% are single or 26.5% are single? It's more logical. Should I say 25% are single or 26.5% are single?
26%.
Because the 5 we don't know. When I use this, my conclusion is not valid. Because I'm telling 25% are single. But what about these people? So this percentage only based on this total does not take care of these values. So this is null and void. So 27 over 102. Whereas here 33 over 108, because all are complete known cases. Are you okay?
Okay.
All right. Any questions? Now, what I'm going to do is, since most of you don't have the software working, I go and take the data and run through some analysis and be sending you the output. You write this final table, right? Example, in this same case, I may run the frequencies. Let's say close this first. Okay. Example, I may just run the analysis, some analysis like this and more analysis. Maybe for BMI, LBP, DBP, these are quantitative variables. Maybe not for test of normality until statistics, this table, right? So the descriptive table, this table for qualitative variables, and this table for quantitative variables. So I'll send you, you're supposed to fill up this table accordingly. These are for qualitative variables. These are quantitative variables. If I choose mean, they're symmetrical. Choose median if they are skewed. So that's your homework for today. I'll be sending this file later. Normally ask the student, do yourself, fill up this and send me. Now with the shortcoming of the software, I'll do the analysis, send the output. You have to do it, prepare this table. Is it okay?
Yes, sir.
All right.
Okay.
Professor, can you show it's like how this data is being fed into this software?
How the data is?
Imported into this software.
Oh, important. Okay. Okay, are you well versed with Excel?
Yes.
Okay, suppose you enter the data in Excel. Let me take some Excel data. Okay, this Excel data, right?
Yeah.
Or make it something simple, easier to see. Okay, this is my variable A, B, C, D, and so on, right? This is my variables.
Yeah.
The first row will be variables, but don't leave any blanks in between. Like I say, gender of, don't write too long, gender of respondent, don't write like this.
Okay.
Just write gender. If at all you need dot respondent, don't leave any space in between. Here no space, right?
Yeah.
Here the space. Don't leave any space in between. Right, general guideline, right? Okay.
Yes.
Okay, let's say I enter the values now. Of course, this can be age. Let's say this is age. This is height. This is weight, and so on. This is your employment status. Okay, these variables. Age, respondent, the height, okay, and the weight. This is 80 kg. All right. Employment. Let's say yes for working, no for not working. Employed, yes, no. Gender, the male, female, right?
Yeah.
Okay, that's a simple data set. So it can be many more. This way, they are variables. This way, they are cases. Doesn't matter how many. Okay, save the file. File, save as, let's say save in the desktop. Okay, I'm saving as book 1. Now go to SPSS. In SPSS,
yep.
Go to File, Open, Data. File, Open, Data.
Okay.
So my data is not SPSS file, it's Excel file, isn't it?
Yes.
This is Excel file. Location, desktop. Okay. So that's my book 1.
Book 1 is.
What? Okay, sometimes the book 1 could be several sheets, right? A, B, C, right? 1, 2, 3.
Yeah. Yes.
Let's take the first one. All right. So data already here, right?
Yes. Okay.
So whenever there are quantitative variables, will come numbers. Qualitative variables will come as you type there, right?
Yes.
Employed, yes, no. So this is your variable view. Right, decimals, I think height, 2, right. This one you don't have. So that's your data, ready for analysis.
Okay, okay.
So
yeah.
it's okay to enter data in Excel, right?
Yes.
Excel available everywhere, enter.
Yes. Sure. Thank you. Thank you.
All right. Any other questions? Okay.
What is the, can I know, what is the standard error which comes when you
Okay,
do
standard
the
error.
analysis?
All right. Okay, later when you do inferential statistics, that's important. Now, since you asked here, what is standard error? Right. So in the analysis just now, we have mean. Okay. Right. So what is standard error? So the mean, this one here, is standard error. Standard error equals to standard deviation divided by square root of sample size.
Yes.
What sample size for this data? 109, right?
Yes.
Roughly 100. Square root
Yes.
100?
10.
10. So 15 divided by 10. That's the value, right?
Yes.
So, but you don't write mean plus or minus standard error. We write mean plus or minus standard deviation. So once you tell the reader the sample size 108, he or she wants to know this, take the value, divide by square root sample size, you get this. This standard error is used for inferential statistical data. Okay? But right now, to describe, we use standard deviation.
Okay.
All right?
Yeah, yeah. Fine, fine. Understood.
Questions? You want to stop here for today? Or you want to do one more? I think you do one more, right? The other notes are sent. Yeah.
So, Prof, for the homework, do we need to email to you, or it's done because you explained it to us earlier on?
Yes, so don't need to email. You just complete. Yeah. The homework today, you don't have to email. All right?
We
to email.
Okay, noted, Prof.
Yeah. Just fill up. At least you know later when you're doing your thesis, chapter 4, how to prepare the demographic table for the table 1. First, you must tell who your respondents were. Whether it's a survey or is it lab study, whatever, you must tell characteristics of the samples. Okay. Okay, take 5 minutes break because it's very important area to discuss and then be useful for the next classes. Inferential statistics. We won't go in detail. Roughly what is, just now we talk about p-value. So what is p-value? Right, you need to know that.
Prof, will you be explaining about the first assignment today?
No, next week, next Tuesday.
Okay.
All right. I may not be following the timeline given by then. Not much been covered. Right?
Okay, sure.
All right. Okay, take 5. We'll continue with this afterwards.